All right, whoops. Welcome back to operating systems. So today we're going to do some basic IPC. Anyone remember what IPC stands for? Inter-process communication, correct. So by default, remember processes are completely independent and we need some mechanism to communicate between them if we want to share any data. And that's what IPC is. So we'll look at some basic ways to do IPC. And spoiler alert, you've done them already because you've read output from a terminal before. So just remember that IPC at the end of the day is just transferring bytes between two or more processes. So even reading and writing files is a form of IPC. The two processes do not need to be running at any given time. So you hopefully have written programs like this that have opened a file, maybe modified a file, and then later ran again, that opened a file, read a file. So technically, that is IPC. You transfer data between two processes, and they weren't even running at the same time. So primarily, the read and write system calls are a way to just transfer bytes, and those file descriptors, well, they could represent a file, and that would be a form of IPC. So let's write a simple process. So a simple process could just write everything it reads. So it could just read from standard in and then write to standard out. That might seem like a silly program, but it's actually very, very useful. So let us go into the code and see this read and write example. So in this read and write example, we'll just declare a buffer of chars of size 4096. We'll see later why this number is important, but trust me, this is a good maximum number to have. And we'll declare a space for a sign size t because read returns the number of bytes read. So we're just going to do a read system call here in a while loop. So it will read from file descriptor 0 and then try and fill that buffer up to a maximum of size of buffer, which is just 4096. And it will assign it to bytes read and then check if it is greater than 0. So if it's greater than 0, that means we read some bytes. Otherwise, if this isn't true, well, we would have read 0 bytes, or we would have read -1 bytes, which is an error message. So let's assume we actually read some bytes. Well, we're going to write to file descriptor 1 using that same buffer with however many bytes we successfully read in. And then we just check the return value to make sure that there was no errors. If there was an error, we'll just capture it, do the p error, and then do a return from main with that error no, so we can actually see what that exit status is and see what the error is. Otherwise, I just have an assert here that the bytes read is equal to the number of bytes written, so I'm not losing any data here. There might be cases where system calls, the write system call isn't guaranteed to actually write everything you ask it to, but for the purpose of this example, I'm going to just assume it does and then write an assert. And you should probably start programming like this because there's a lot of underlying assumptions you might make. And the easiest thing to do is just to put them in an assert if you make an assumption. That way, if you screw up or that's no longer true, instead of being impossible to debug, it will just say that assert is no longer true, and you'll have to work around it. And you actually know what's going on. All right, otherwise, if it exits the loop, I check if bytes read is equal to -1, which indicates an error. And then otherwise, I just assert that bytes read is equal to 0. And you might see here that, hey, this could be a file. I'm not checking for end of file or anything specific. There's no special end of file character. You might have been taught that before. When you get to Linux, that is not true. So the way Linux signifies that there is an end of file is if you call read on it, and it just returns 0 bytes read. That means there's no more data. It's not possible to get any more data. You're at the end of the file if it represents a file. So any questions about this example? So let's go ahead and run it. So if I go ahead and run it, it does nothing. So that's what I would expect because it is reading from 0, which is standard input, and I haven't told it to do anything yet. So if I go ahead and type, I could type something like hi and then press enter, and then suddenly I get it shot back to me, right? It would read my input, which was the string hi with a new line, and then I press enter. The read system call would actually read the data, and then it would do this, and then it would write that data right back out to standard out, so I see it twice. Any questions about that? Or why this would be useful? Has anyone encountered a program that does things like this before? Does this remind anyone of something? Yeah. Copy paste, very close. You can actually use this to copy files if you really want. We'll see that shortly. Has anyone used this command? So guess what? If I run this command and I say hi, it does the same thing because this program actually just does what I wrote. It just reads from standard in and outputs to standard out, and that's all it does. Yep?
So for bytes read equals 0, do you just have an empty line?
So for bytes read equals 0, it means I've read every single byte from the file. So in this case, since I'm typing into it and it's not a file, you might be like, okay, well, how do I tell it that I'm done? Is that your question? Yeah. So if you want to tell it you're done in standard input, I can press Control D, and Control D closes your standard input, and then that program would have read a 0 and then closed. So cat would do that, and my read-write example does the same thing. If I press Control D, it gives me my terminal back. So that simple application is actually pretty powerful. So let's see other things we can do with it. And yeah, just to recap too, so read just reads data from a file descriptor, and it's an abstraction, so you're not actually sure what that file descriptor represents. In the case that I've showed you so far, it just represents me typing into my terminal. And like I said before, there's no end-of-file character. That is not a thing on Linux. The read system call will just return 0 bytes read, and that's how you know it's not possible to get any more input. And again, you should probably check for errors here. We'll see a case where checking for errors is probably a very good thing. And yeah, this screen's at a weird place. So yeah, cat's short for concatenate because we can actually use this to concatenate files just by using those file descriptors. So the write system call just writes data to a file descriptor. Same thing as read, returns the number of bytes written, and you shouldn't always assume it is successful. And again, if you want to see what the error no is that caused it, well, you probably have to save it because that p error function might set it, other functions might set it. So if you want to capture that error, you have to save it before you call any other function from the C standard library. So, and also with this, I'm reading from standard input. So another process is writing to that same file descriptor, which is why I can read from it. So my terminal is taking the keyboard input I put in and then writing to that file descriptor, translating it to ASCII, and then that process can then read from whatever it wrote in. So both sides of this are going to have a read and a write side. In this case, we're just dealing with read from standard in and write to standard out. So these are pretty powerful. So what we could do is we could close the standard output, just freeing file descriptor 0, and then we can use that open system call to open a file instead. And Linux has a rule here with file descriptors, so it will always use the lowest available number whenever it needs to allocate a new file descriptor. So if I close file descriptor, so by default, 0, 1, and 2 will be open. If I close file descriptor 0, then suddenly 0 is available. That's the lowest number. If I open a new file, it will just get file descriptor 0. So we'll essentially replace standard in. So let's look at that example. So this code is going to be the exact same, except I take another argument from main. So if I have a second argument that's supposed to represent a file, I will close file descriptor 0, and then I will try to open whatever that file name is as read-only, because I'm just doing read system calls on it. And then here I would check for an error. If there's not, then I would have a file open as file descriptor 0. So if I go ahead and run that, I can go kind of meta here, and I can tell it to read the source code file of itself. So if I execute this, what should I expect to see? Yeah.
Source code in the terminal.
Yeah, I should just expect to see the whole source code. So there's the whole source code for it. So now, because of that, the rest of the program didn't change. It's just reading from 0 and writing to 1. But all I did was replace 0 instead of being the default thing where you just type into your terminal, and that's what represents file descriptor 0. I replaced it with an actual file. Yeah.
Maybe I didn't see the whole program, but I don't think do you have to close file descriptors?
So the normal convention is that file descriptors 0, 1, and 2 are open and you don't close them.
Even if it's another file? Like even in this case where you opened another file and replaced file descriptor 0?
Yeah, even in this case, because I use it until the end. So it's like that whole thing where we don't have to necessarily call free because the process is going to die, then everything gets cleaned up. So this, we don't have to do it. Yep. Yep.
What if you, and then you open like a new file for file 0?
Yep.
What if you open the standard in again? Would it take, it's like 0 place again, like file descriptor, would it include 3?
So yeah, the question is, if here I close file descriptor 0 and then I open it again, what would happen? So we actually don't know what file descriptor 0 represents in general in this case. So it gets like a special file that represents my terminal. And if you knew what that was, you could reopen again and nothing bad would happen, but you would have to guess it. So if that's my only way to refer to file descriptor 0 and I close it, I can't get it back without knowing how it got opened originally. Yep.
So if you were to open a file descriptor that's not 0, 1, or 2, like maybe in a loop or something, and you close them, like you close them in the same loop, would there be a way to check whether there are file descriptors open?
Yeah, so you can check whether or not there's file descriptors open. In fact, that's what one of your test cases does in lab 1. So I check that you close your file descriptors because you should, they're like memory, you should close them whenever you're done using them. So you should, but by default, no one closes the default file descriptors 0, 1, and 2. So, all right, any other questions with this? So this, yep. What the difference between argc and argv is? So here, the C way of referring to things in main, int argc is the size of this array. So it's however many command line arguments you have in it. So in this case, by default, the first one is always going to be like how you ran it. So this would be the 0th argument, this would be the first, and there'd be 2 elements in this case. If I did this, then argc would just be 1. Okay, so that actually also behaves exactly, the same as cat. I can cat the file, I get its output. Doesn't really do anything special. In fact, if you use the standard file descriptors, you don't even have to write open and close to deal with files. You can do some hacks with the shell. So in the shell, I can do something fun like just use, my first version that just used 2 file descriptors, and I can use this fun arrow and give it a file. So what this will do is your shell will actually open that as a file and then replace file descriptor 0 with that file for you. So now suddenly, without changing your application at all, it can deal with files if you just use the standard file descriptors. So if I run that, it's the exact same thing. And then I could also do something like this. So the other arrow will replace standard output. So this goes to whoever said it's kind of like copying. I could do something like this. So I could replace standard output with a file as well. So this will read from one file and then write to another file, which is AKA copying a file. So if I do that, and then I look at copy.c, I should see that it is exactly the same. So using this, you can use cat to actually copy files if you really wanted to, which is kind of neat. At least I think so, but I'm me. All right, any questions? Yep.
Where did you write the logic for the
So the question is, where did I write the logic for this? So the nice thing about it is you don't have to write it. So your shell will do this replacement. So this is just a shortcut. So before it creates this process, it will open file descriptor. It will open this file and then use this as file descriptor 0 for that process I'm about to make. And then it opens this file and replaces file descriptor 1 in the process I'm about to make. Yep. No, it doesn't change argc, argv, or anything like that. It just changes the standard what the standard file descriptors actually refer to. So if I do this, instead of before standard input was my terminal and standard output was my terminal, now standard input is openexample.c and standard output is copy.c. So if you want to capture the output of any program to a file, if you haven't seen this before, you can just do like that. I might have showed you that before and not explained it, but this way it just captures the output of any program by just writing it to a file instead of the terminal. Yep.
What if your program has like scanf or something, and then you try to put like the change the file descriptor to like some file or something?
Yeah, so if your program has scanf or something, that's just going to read from file descriptor 0. So if you give it a file, it will try and scanf whatever match the format. If it doesn't match the format, it'll give you an error. So it'll work the same way. Scanf works fine. Yep.
So if you want to output something to a different file, a text file, does it have to be created, or it'll create one if it's not?
Yeah, so this will create it if it doesn't exist for you. So that's part of your shell. These are just fun shell extensions that they've written over the years. If you want to, you know enough by now, you could write your own shell if you really wanted to. It's kind of cool. Yep.
Sorry, just to confirm, so which means when you do that, you kind of replace the standard file descriptor 0, for example.
Yeah, so this arrow replaces file descriptor 0. This arrow replaces file descriptor 1. Yep.
What happens if you have multiple opens back to back?
So if I have another open, whoops, how did I screw that up? Like if I just open something else here.
Yeah. What happens? Well, and then you change FD to FD1, int FD1. What happens to in the beginning of that line, instead of FD equals open, you do int FD1 equals open, and whatever you have.
Int FD1 equals open.
Yeah. What happens if you do this?
So it will just open that file, give you a new file descriptor. In this case, I can argue that it would be file descriptor 3 because that's the lowest available number. And if I want to write to that file, if I wrote to file descriptor 0 or 3, it would do the same thing. They both represent the same file. Yeah, so you could have multiple ones. You could have, you could have it really screwy where standard input and standard output refer to the same file, in which case bad things will probably happen. We'll save that for later. But yeah, these standard file descriptors, they're actually pretty powerful. And that's why they designed Unix like this. So yeah, so here's what we saw, where we saw that the shell lets you redirect the standard file descriptors. So I didn't actually have to write a program that did any open system calls. If I'm just using file descriptors 0 and 1, well, I can just let my shell replace them for me. I don't have to write any additional code. And you don't have to, like, if you want a program to start using files instead, you don't have to modify it or anything. You just use shell commands. There's also this fun operation here, which is a little pipe operator. So this actually feeds the output of this process into the input of this process. So anything that it writes out gets read by the next one in the sequence. So if I run something like this, oops. So if I run something like this, I'm going to get the same output, but it's going to be a bit more roundabout. So cat openfile.c, well, that will print the file to standard output, and then this operator would redirect that process's standard output to the next process's standard input. So this would read all that information again and then write it out to my terminal. So this is how you can chain commands together to do some special stuff. So like, for example, if I did like ls-l, that gives me a new line for every file in my directory. If I want to count how many there are, well, there's this other program called word count, and you can give it -l, and it counts however many lines it reads in. So if I do that, I can see, hey, I have 12 lines here, and you could do that for any one. In fact, that's what I use to figure out how many thousands of system calls JavaScript did. So I just counted the lines using that program. I never wrote a program that counted lines. I just reused that one and just moved the outputs around. Okay, so all right, so now we get into signals, which is another form of IPC, and they basically behave like interrupts. So, has anyone ever ran a program before and it ran too long, or your thing got in an infinite loop and you press Control-C? We got some. Does anyone know what Control-C did? No, we just know to hit it. Yep. It does interrupt your program, but specifically, it will send a signal. So, let's see. So if we go here, let's just see that it works. So, whoops, build, open example. So I'm going here. Oh no, I don't know how to exit. I press Control-C, and it exits. Well, I can see it didn't actually reach end of file or anything. If I put some print statements at the end, I can see that it didn't finish my process or anything. It just kind of ended. And that seems a bit weird. That's not super satisfying. So what actually happens is when you press Control-C, the kernel will send a signal to that process, and in this case, it gets a name where it's called signal interrupt. So it's a special signal to represent the user interrupted the process through using the keyboard. In Python, it's just called keyboard interrupt, I think. And all the signal is basically the kernel generates an interrupt to your process, and then each different signal is just assigned a number. So sigint will just be a specific number, and the default handler. So there's a default handler if you don't write one, and by default it will exit the process with the exit code equal to 128 plus whatever the signal number is. So if I go back to this, I can see this is my exit code way in the bottom right here, this 130, and I didn't call exit with 130. That was the default signal handler that actually exited my process with that exit status. So since it's 128 plus whatever the signal number is, I can probably, hopefully we can do some math and argue that sig int is signal 2, because 128 plus 2 is 130, which is what I saw. So we can see that this is what's actually happening. So we've all written interrupt handlers. Well, you have written interrupt handlers, so signals and dealing with those are the same thing. You can write your own interrupt handlers. So you write your own signal handlers and then you register them through a sig action system call, and we'll see an example of that. Basically, you just declare a function that doesn't return a value or anything. You should be fairly familiar with this for any interrupts you have, because they just get called asynchronously. And all it has is an int argument that represents the number of the signal number. So some of the numbers are non-standard. Below are some of them from Linux. So 2 is interrupt from keyboard. 9 is sig kill, which is a fun one that we'll get into later. Here's another fun one that you've probably encountered before. Segv, so segmentation fault. That is you dereferencing a null pointer and those fun stuff. So that is just a signal. And by default, that's why your program dies, because the default signal handler just exits your process, and it would exit with 128 plus 11, so 139, if you've ever actually checked it whenever you segfault. And then there's this 15, which is sig term, which is terminate. And that's supposed to represent graciously shutting down, and we'll see what not graciously shutting down looks like. So let's go into this example. So in signal example, so I'll just keep the rest of the program, so it's just going to read from standard in and write to standard out. And in here, I just have a register signal that just creates a sig action struct. So they give you a struct to fill in. You can use this function to zero initialize it. And then the only argument we really care about is this SA handler. So it says, what function should I call whenever I receive a signal? And here I just have this handle signal, and I'll just do something stupid, and I will just say, I will ignore you, because if we register a signal handler, we can do whatever we want. So this is actually a good way to annoy your friends. So in here, we do the sig action call, register a signal number, and then say the action, which has our handler we want to run, and then we just check for errors. So in our program, we're going to register a signal for sig int, which is pressing Control C and generating that, hey, I want to interrupt you, I probably want to quit. And we'll also register the signal handler called sig term. So if I run something like this, and I run it, well, it behaves as before, but now what happens when I press Control C and your friend wants to get out of your process? Well, just ignores it. That's fine. So this is a good way to annoy your friends, because, hey, it's not going to exit. So one way we can actually try and exit, we can try to exit it nicely. So we can ask PID of and then give it a name. So it was called signal example. This program gives you the process ID of any processes with the matching name. So here, this is the process ID for that program, which is still running. And you can actually send signals to any process you would like. And this is where our friend sending a signal is called kill. Why is sending a signal not called send signal, and why is it called kill? I have no idea. But by default, it's called kill. So I can say kill this process and then go look over at, and then it says ignoring signal 15. So kill by default just says please close nicely. That's that sig term, which is 15. But as luck would have it, I ignored that too, because yeah, why not? Right, I could ignore it. So there is a special signal that you are not allowed to ignore that will kill your program, and that is this -9. So -9, this dash and then number will send a signal of that number. -9 is sig kill. That is a signal you are not allowed to handle. So the kernel handles this signal for you and has its own handler for it, and you are not allowed to overwrite it. So if I do kill -9 to it, and then I go back over to it, I see that it was killed. So now we have the word kill in our vocabulary, so we can now kill our children. Yay! So, any questions about that? So that is a fun thing to do. And by default, sometimes whenever you're writing this, so before I rebooted my computer, that example behaved a little bit differently. So whenever I hit Control-C before, it actually stopped running because the read system call returned an error. There is sometimes system calls can return an error that say they got interrupted and they don't automatically restart by default. In this case, it did restart by default. So we should have saw something like ignore signal 2, and then it would have gone back to executing our program, and we would have saw that read got an error, and its error would be interrupted system call, in which case I modified it in another example that checked for that error and then would restart the read system call, since that's actually not a bad error. That doesn't mean anything's gone wrong. That just means I have to retry the system call. And then, so that's where that example is. And now, if I fix it, it does the same thing I showed you where I just press Control-C over and over again, and I can't get out of it. And here is the explanation of what I did before that. So sending a signal, the system call is called kill, and someone wrote a program called kill that just essentially does that kill system call for you. So you can, so it takes the number and then the PID of what to kill, and I showed you how to find the process ID with PID of. That is another program you can run. And then after, kill with just a PID sends sig term, which is supposed to just say end graciously, please. And the idea behind that is you can register a signal handler and do some cleanup and, be sure you don't mess up your files. You write anything you need to write before you exit, and then you just exit. Then we saw kill -9, which that's like you're telling the kernel to kill that process, and it doesn't have any rebuttal to it. It just kind of dies. And yeah, and then there's a question, can you override seg faults? Sure, you can ignore them, but then the kernel, if you catch it, the kernel thinks that you should fix it because it will try and resume running your program. So if you catch it, you do nothing, and then it tries to resume your program and just seg faults again. It'll probably get very angry at you and just kill it because it can't run anymore. But if you really wanted to, you could catch sig fault if you want. So it probably won't help you. It's really hard to recover from that, but you can if you want. And yeah. Yep. Yep. Yeah, so if I get PID of and I have 2 processes with the same name, it'll return all of them. So it would return both of them. Yep. Okay, so that's fun. So I talked earlier too about blocking and non-blocking operations and that wait system call. So let's see that. So A non-blocking system call is going to return immediately. Remember, by default, the wait system call is going to wait for your first child to terminate before it returns. But if you don't want to wait for that, you can do a non-blocking wait. So you can turn it into non-blocking by using wait PID. And then there is another argument for options. And one of these options is this W no hang. So W no hang means not blocking. I just want to see if I have any terminated children. And to react to these, well, there's two options that you should probably recall from architecture, pulling and interrupts. So let's go ahead and see what the pulling example would look like. So, So here's code we had before where we have main, we immediately fork, and then the child sleeps for 2 seconds and then exits. And now in the parent, we'll set up wait PID, we'll initialize it because why not, and then set up some space for the status. And now I'm just going to see how many wait system calls we actually need to make. So here, I just have a count I initialize to 0. And then while wait PID equals 0, which means for the non-blocking version, a child hasn't terminated yet. So I'll just have a loop that says, well, I don't have a child terminated yet. Just go ahead and call wait PID with the status that we used before, and then no hang. And in this case, I'm specifically waiting for a certain child to terminate, because in this example, well, this child process just has this parent process just has one child anyways, so I can just wait for it specifically. If I wanted to do a non-blocking wait that waited for the first children to die, like wait, well, I would just do something like -1. So -1 means wait for the first child. But in this case, they're both going to do the same thing, so it doesn't really matter. So if I run the pull example, well, it's going to ask over and over again. It should be asking for 2 seconds, and let's just see how wasteful that is. So it's just asking out over and over and over and over and over again, and pulling, and it asked 370,000 times. So it did 370,000 system calls, which are pretty slow, and just asked, hey, is the child terminated yet? Is the child terminated yet? Is the child terminated yet? Which seems really bad. So how would I make this better? So this is wasting a lot of time. What could I do to make this not waste so much of my CPU? Yep. While still pulling over and over again.
Then we can wait before pulling again instead of just pulling for every cycle.
Yeah, you could just like sleep. Like that? Yeah, so this will work better, right? Oh, I typoed the other one. Oops. Which one did I break? Oops. There we go. So if I do that, I'll get one attempt, another attempt. Oh, yay, it finally worked. But this is going to be also really slow because I sleep for a second. I won't immediately get notified whether or not the child terminates. I might be up to a second late. Hopefully on average, I'm like half a second late, but that delay is probably still is probably bad. So the optional thing to do is to do an interrupt version of that. And in user mode, the interrupt version of that is signal. So remember how I told you that, hey, when one of your children terminate, the operating system pokes you? Well, that poke it sends you a signal that says, hey, you have a child that is dead or terminated. Sorry, not dead yet. So in here, I can have a handle signal. So I'll just register a signal handler. And there's a special signal called sig_child, which has another number associated with it. So that is the signal you get when the kernel wants to tell you that your child has terminated. So in here, in my main, my child's going to do the same thing, so I'll wait for 2 seconds and then terminate. And then here in the parent, just to show that I can do useful work, I'll just print off I'm going to go to sleep and then sleep for 9,999 seconds, just to show that, hey, this could represent a long-running task, and an interrupt is instant, so it will interrupt this sleep. So I register the sigChild signal handler, and in the function, that's where I actually call wait. So I'll call wait with wait PID, give it -1 because I don't care, it's the first child. In this case, I'm not keeping track of the child's PID I created, so I don't know what it is in this function unless I create a global variable or something like that, but I didn't. So I'll just use -1 to say just the first child, even though there's only one. And then here, I just call wait PID with the no hang, and then check if there's an error. Otherwise, I'll do the same thing and just print off whatever I got. So if I run this, it should be a lot faster. So I just say time to go to sleep, then 2 seconds, the kernel generates a signal for me, I handle it, I wait immediately, I'm a good parent, I immediately took care of my child, even though I was doing something else that you might have thought was more important. So any questions about that? Yep.
Sorry, could you explain why you set it to -1 bit during the wait version?
Yeah, so the question is, why did I set it to -1 here? So I set it to -1 here because in this signal handler, right, it just gets the number of the signal I got. It doesn't get any other arguments. I can't pass any other arguments to it. So I don't know, I don't have any access to this variable. So I capture PID in the parent, but in that signal handler, I don't have access to it. If I wanted access to it, I could make it a global variable or something like that, but I decided, well, I can just wait for any old child. I don't have to create a global variable or do anything like that. So I could have, but I didn't want to. All right, any other questions with this? Yeah, and good parents, yeah. If you want to be a parent, you just have to acknowledge your child. You can neglect it its entire life. You don't have to constantly hover over it. Just wait for, a sensible adult like the kernel to tell you that, you should take care of it. All right, any other questions with that? Cool, so everyone knows signals? Yep. Sorry? Like the handle? Yep. So it's pretty much what I had in all the examples where I just say I'm calling wait and just call wait. In this, the only difference is instead of just calling wait, I called wait PID with -1 and used the no hang version. So if I didn't have a dead child, it would just immediately return with 0 to say it's still running. But in this case, the kernel already told me that it's done, right? So I can just do the no block version and it should return immediately. Yep. Yeah, so if I have multiple children, I could get multiple signals. Yeah, -1 would still work. In fact, if you have multiple children, you don't know which one's going to terminate first, unless you really wanted to wait for one to finish before the other for some reason. You could do that by waiting specifically on their process ID, but if you don't care, you just want the first one, just -1. Yep.
So, which means the difference between like what you did with signals at the last lecture is that you don't call wait until the signal is set. You don't need to like block it. The parent doesn't need to wait.
Yeah, so in this example, my process could do useful stuff instead of just calling wait and then waiting for the kernel to wake me up. Sometimes you might want to call wait. Sometimes you're just managing processes and you just want to wait for that specific one to finish and you don't have anything useful to do. This one, I had useful things to do and I wanted to be notified immediately. So it just depends what you want to do. Okay. So, Yeah, so we saw the interrupt version, the polling. And so now we have to talk about interrupt handlers, and they run to completion, and you can generate multiple of them, and they're not great. So let's see an example. So let's have our open example. Well, we might want to write it in such a case that if we get a control C, we might try and be good upstanding citizens and close our file descriptor that represents the file before we exit. So in this case, if I have an open file descriptor in my signal handler that will catch me pressing control C or asking to terminate, I'll print a message that says, I'm going to close this file descriptor and exit. Check if the file descriptor is equal to -1, and the file descriptor is a global variable, so I can access it in this handler. So my main function will set this file handler if I give it a file argument. And then in here, I'll just say close. Basically, all I want to do is close that file descriptor in the signal handler. And then I'll check if there was an error. Otherwise, I'll say, closed file. Then I'm going to artificially slow it down to illustrate something, and then I'm going to exit. So, all looking at this, we could just say, hey, if I press Control C or I ask it to terminate, everything should be fine, right? I just close the file and then close the process. I should never get an error from close. Well, in fact, that is probably not a thing. So let's signal close example. So here I say what the process ID is, just so I can send signal to it easier, and it will say, hey, it opened file descriptor 4. So I didn't actually close file descriptor 0. Then here I can be nice and say kill that process. And then it says, hey, I closed the file, but then I can press Control C. And now that signal handler runs again. So in the middle of that signal handler, a new signal handler runs before that one is finished, and it starts doing the exact same thing again. So the first signal handler would have printed, then closed the file, and then print closed file, and then been in this sleep. And then while it was in this sleep, we started another signal handler while this one was sleeping that did the same thing. So it printed this, then it tried to close, and guess what? It got an error, so it hit this, and then did P error with close, bad file descriptor, exit. Why was it bad? Because we closed it already, right? So this kind of sets the stage for threads later. This is an example, kind of an example of concurrency and things you have to be careful of. So signals like this, things like this are possible, which makes your life very difficult. So we'll get into that. This is just kind of a warning as something not to do. Technically, the terminology when we get to it, so just so you remember it, this is called your signal handlers have to be re-entrant. So in the middle of calling it, you need to be able to call it again, and it needs to be able to successfully finish. In this case, not really the case. All right, so before we close, so that was, real quick. So your hardware interrupts are a bit different. So on RISC-V, there's like 3 terms for an interrupt. And it depends how it got generated. So there's an interrupt, which is triggered by real external hardware, like a keyboard or something. The kernel handles that. You don't see it in user mode. Then there is an exception, which is essentially the same thing as an interrupt, but that's caused by you executing an instruction you shouldn't have, like divide by 0 or referencing memory. And the kernel may pass that up to your user process in the form of a signal. And then there's a trap. So you're just requesting control that can be caused by an instruction or something like that. And a system call would be an example of a requested trap. So you are triggering an interrupt that the kernel handles. All right, so before we leave, so I always get this and I always hate this part, but you might ask, hey, Process ID 1, pretty special. Kill-9, pretty cool. What happens if I do that? If I just kill-9 1, anyone want to guess what happens? Yep.
Everything shuts down.
Nothing shut down. Why is that? Oh, I didn't get a good warning. Anyways, so the kernel actually protects you from kill-9ing init because it knows that's a silly. It has a shutdown command for a reason. So newer kernels won't let you do something silly like this. But I can do something sillier and still break it. So systemd, remember, that's the thing controlling my whole root or my whole user. So I could wreck this VM and do something, I don't know which one's which. I could do this, and I meant it. All right, that was the wrong one. Hey, it's still going. Oh, it just restarted itself. Cool. All right, cool. It's resilient to this. So I'm not actually logged in directly to it. Visual Studio Code's doing some magic, which actually saved me from it. Wow, this example sucks this year, but sorry. All right, just remember, pulling for you. We're on this together.